All right, good morning, everybody. Everybody doing all right? Well, good. Well, welcome to day 2. Glad you came back. We're going to talk today about Chapter 1. So Chapter 1 is just a one-day presentation, so we got a lot of information to cover today. Again, we're not going to cover everything in excruciating detail. And as we move on into other chapters, things that I think you need to have a little more information on, we'll do what I call just-in-time teaching, and I'll get you what you need. Again, this is largely kind of stuff that you kind of picked up some of it in general chemistry. Most of this was covered, I think, in 250. Excuse me, we were in 251. In 106. So we'll cover this stuff today. So a lot of things. We're going to talk about atoms, or atomic structure, where electrons are, how atoms bond together. We'll talk a little bit about Lewis structures, talk a little bit about orbitals. We talked a little bit about that last time. We started talking about rooms for electrons, but we didn't go into it a whole lot. Talk about covalent bonding and functional groups. Now, Chapter 1 also talks about ionic bonding. I'm skipping that. You all can review that on your own because most of what we deal with in organic chemistry is covalent. So, again, I'm trying to cover the top stuff. And then we'll talk a little bit about functional groups. And functional groups is a very important topic for you all. The amazing thing about organic chemistry is if you know your functional groups, you can predict a lot of stuff. There are lots of functional groups. We won't go into that many of them, okay? So you won't have a whole lot of stuff to memorize. But functional groups are one of those things, and I don't say this very often, but functional groups are one of those things that you will have to memorize. You need to know your functional groups, okay? So the functional groups that are covered in Chapter 1 are definitely going to be important throughout this semester. Okay, so let's go ahead and jump in and get started. So let's talk a little bit about modern atomic theory, right? And so you all know that atoms have this structure, right? You've got protons, you got neutrons, and you got electrons. And if you go and you talk to physicists, they'll also say, well, but those things are made up of quarks. I don't care about quarks, okay? We're going to be talking about protons, neutrons, and electrons. And what did I say on Monday? The chemist is most concerned about which one of these particles? Electrons, right? So of the electron, in my professional opinion, from my perspective, is the most important of the subatomic particles because it is really what determines the chemistry, okay? So, ooh, that doesn't look very good on the screen, does it? I'm sorry. So you all know about a proton. For whatever reason, I made protons blue. And you'll see that they have a mass of about 1.67 times 10 to the negative 27th kilograms. Pretty small amount of mass, but that's where a lot of the mass of an atom comes from, right? And then you have neutrons, right, which are neutral, and they have a mass of about 1.675 times 10 to the negative 27th kilograms. And then you have the tiny electron, right, and it has a negative charge. It has just as much negative charge as a proton has positive charge in terms of the magnitude, right? And the mass of the electron is really negligible. It's 9 times 10 to the negative 31st kilograms. So what's kind of interesting about the neutron? No charge. What else? It does have mass, and it's almost the same mass as a proton, but not quite. But not quite, right? In fact, a neutron is nothing more than a proton and an electron that have combined. That's how you get neutral charge. In fact, beta decay in nuclear chemistry is when a neutron spontaneously decomposes into a proton and an electron, and it emits the electron, okay? But it's not even quite that mass if you add them up. There's something special going on with the neutron. The good news is we don't need to know what that is. It has to do with quarks. But it is kind of an interesting thing that it doesn't quite add up, right? So you got to know a little more physics to completely understand what's going on in the nucleus. And again, chemists don't really care about the nucleus. We care about the electrons. So we'll focus on that. And the way that I like to think about neutrons is that they are buffers for protons. So think about it. You've got this small thing we call the nucleus, and you're trying to put a bunch of positive charges in there. What do we know about charges that are like charge? Do they attract each other or do they repel each other? They repel. We know that like charges repel, right? So how do you get all of those protons into this dense small area? You start packing some neutrons in it to shield it. And that is, my physics friends would kill me saying it that simple, but that's really functionally what's happening, okay? So these neutrons help shield the protons from one another so that you can actually build a nucleus. And the nucleus is there so you can have places to put electrons, right? So the bigger the atom gets, the more protons you have, the more neutrons you need to go around and help shield those protons from one another. It's the way I like to think about it. Now, you will have, of course, orbiting, if you will. That's why we call them orbitals. And not orbiting like a spacecraft or anything, but it's one way to think about it, right? You have one or more negatively charged electrons that are floating around outside the nucleus, and it turns out that they can't just float around anywhere, right? There's specific places for them to be. Those are the orbitals that we'll talk about. And we know that in an electrically neutral atom, the number of electrons must equal the number of protons, right? So if I don't have an ion, so if I just have carbon, right, I know that the number of electrons are equal to the number of protons, and so that makes the overall atom negatively charged, or neutrally charged. Okay? So, let's talk a little bit about orbitals. Last time we talked about s orbitals, we talked a little bit about p orbitals, and I mentioned there were also d orbitals, and there's actually other orbitals, there's f orbitals, right? But for organic chemistry, we only care about the s and the p, so that's really what we're going to focus on. And so what you can see is an s orbital. It's easy to remember what s is because s is the first letter in sphere, right? It's a spherically shaped orbital, okay? And what you're seeing here is just an example, just a ball, right? So that electron can be anywhere within that ball, right? It has a probability of being in that orbital, right? Now the p orbitals are kind of dumbbell shaped, right? And you'll see that you have a px orbital. What does that mean?
On the x-axis?
It's on the x-axis. We have a py orbital, which means it's on the y-axis, and we have a pz orbital, which means it's on the z-axis. So remember, in your Cartesian coordinates, you have x, y, and z, right? That's how we define three-dimensional space. We have three orbitals that are just pointing differently. One's pointing this way, we call that the x orbital, the y orbital, and then we have one that's coming out of the plane of the board and behind the plane of the board that we call the z orbital. Okay? Those orbitals are also called degenerate orbitals. What do we mean by that? We mean that they are the same energy. They're just pointing in different places in space. That's all it is, okay? But they're called degenerate, okay? I know degenerate doesn't sound like a very good word. When you call somebody a degenerate, that's usually not a good thing, but it's actually not a bad thing in atomic orbitals, okay? So, what's the little dot? It's the nucleus. And what do we know about the orbital and with respect to the nucleus?
It's huge.
It is huge, that's true. What else do we know? What does it mean to be blue and red and nothing in the middle? Pardon? They are, okay, so those lobes of the orbital are opposite signs. So they do kind of, one's kind of positive and one's negative. I'm not meaning charge. These are mathematical signs, okay? In terms of the wave function, we're not going to talk a whole lot about wave functions, okay? But they actually have different signs. So this is the positive or negative, however you want to think about it. They just shade them as blue and red. Notice there's no shading in the middle. The electron that is in this particular orbital, if there is one, can be here, it can be here, but it can never be there. We call that a node. The electron can be on the blue side, it can be on the red side, but it can never be in the middle. Never, ever be in the middle. It's zero probability of finding an electron in a p orbital near the nucleus. Is that true for the s orbital? No. The s orbital, the electron can actually get very close to the nucleus. Okay? So that's the difference. So you've got spherical orbital, we call that an s orbital. We've got these 3 p orbitals, and we got each one of them lying on different axes, okay? You also need to remember the Pauli exclusion principle, which basically says that no 2 electrons can have identical quantum numbers, okay? A subatomic particle has to have unique quantum numbers associated with it. We're not going to talk about what those quantum numbers are, but there is an important characteristic of this, and that turns out to be that each orbital can have no more than 2 electrons in it. I don't care what orbital it is, an s orbital, a p orbital, a d orbital, you can only have up to 2 electrons in an orbital, okay? Think about it as a double occupancy hotel room. Can't put more than 2 in, okay? And the 2 that you put in better get along with one another, okay? So that's important. So that's the Pauli exclusion principle. We also have what's called the off-ball principle, which means that we are going to fill the orbitals from lowest energy to highest energy. So when we're doing the electron configurations of an atom, you start at the very lowest energy. Electrons are lazy things. They like to be at the lowest energy they can be, so they're going to fill there first and work their way up, okay? Just like if I asked you all to go to a hotel that had nothing but stairs, you all would want to fill up that first floor first because nobody wants to carry their luggage upstairs, right? Okay. So that's what we're talking about. And then, of course, we just mentioned degenerate orbitals, orbitals that have the same energy. And for the purposes of this class, it's the p orbitals. So px, py, and pz. And so px, py, and pz are 90 degrees to one another. Okay? So keep that in mind. Your px, your py, and your pz are going to be 90 degrees to one another. And that's going to be important when we start talking about shapes. Okay? And then, of course, there's Hund's rule, and that is, has to do with the number of unpaired spins. Okay, so you want to minimize the number of unpaired spins. So let's all do, you all can work kind of in pair up with somebody. How would you fill the orbitals for carbon that has atomic number 6? So if it's atomic number 6, how many protons does it have?
6.
So how many electrons does it have?
6.
All right, so we got to take care of 6 electrons. You all work for about a minute or 2 with your neighbor, figure out where all the electrons need to go. How are you? It's okay.
Also, they didn't give me my book at the bookstore.
Your book is actually in the Canvas shell. You've got an electronic version in the Canvas shell. Yep.
Just making sure I was there. I don't know what.
You're good. It's in Canvas.
Okay. Just making sure. So,
All right. So how do we fill this up? Where do we start? We start at the bottom, right?
Yep.
So that's the lowest energy. So I'm going to put 1 electron, and I'm going to draw it as spinning up. That's what the little arrow means, right? So now what do I do? I've got 5 more that I got to take care of. What do I do now?
Put another one down.
I put another one in 1s, and why? Why don't I move up?
You have to fill it first.
That's right. Yeah, we're always going to fill the lowest first, right? So now I've got 4 left. Now what do I do? So I've taken care of 4 of the 6. Now what do I do?
You do one more on 2
And now what do I do?
The 1 and 2 T1.
That's right.
How don't you put it in the other one?
Why don't I put it here? Because these are degenerate orbitals and we have to at least half fill them before we go back and pair them. Why is that? Why didn't I just go ahead and fill the px orbital? Why did I go px and then py?
Because you have to put one in each plane first.
That's true. But why do you think that is? Think about the hotel analogy again. If I gave you the choice of staying by yourself or pairing up with somebody, which would you prefer? By yourself. The same thing is here. So the electron is going to be spinning up in this room. It's going to be spinning up in that room. If I tried to put them together, one of them would have to flip and go the other way, and that takes energy. Okay, so this is the lowest energy way to do it, is to actually half fill the orbitals before you completely fill them, okay? When you're in a degenerate orbital situation. The only difference in these orbitals is how they point on the axes of a Cartesian coordinate system. Do the same thing for oxygen.
Okay, so same method.
So what am I going to do? I've already taken care of 6. Oxygen has 8. I've only got to take care of 2 more, right? I didn't have to write out another diagram. So what do I do now?
Put another one in 2pz and then another one spinning down to 2pn.
That's right. That is the electron configuration for oxygen. And what's interesting about this, if you look at this, you've got a single electron in 2py, you've got a single electron in 2pz. This is why oxygen behaves the way that it does. Okay? Oxygen has these lone electrons when you make molecular oxygen, which we're not going to talk about. But oxygen is actually magnetic, believe it or not. It will, if you have a liquid oxygen, you put it between the poles of a magnet, it will float there because it has these unpaired electrons that allow that to happen. If these were all paired up, it wouldn't do that. It would just fall through the magnet. Okay? I will frequently give you useless tidbits because I find it interesting.
Nothing's useless.
Nothing's useless? Okay, good. I like to hear that. There are core electrons and there are valence electrons. The core electrons, okay, are those electrons contained below the outermost shell. So we're looking at oxygen here. What are the core electrons?
Nicole's in the middle.
This one, right? These are core. Those are the core electrons. Core electrons do no chemistry that's of any value. Okay? They're placeholders. Okay? So if these are the core electrons, what are we going to call these?
Valence.
That's right. Those are the valence electrons, and they are all of the electrons that are in the outermost shell. And since we're talking about oxygen, there's only 2 shells, the 1 shell and the 2 shell, right? So all of the electrons in the outermost shell, which is n equal 2 here, these are the valence electrons. And so there are 2, 4, 6 valence electrons for oxygen. How many valence electrons are there for carbon? There are 4 valence electrons for carbon. That's what we're looking at there is carbon, right? I erase 2 electrons, I get carbon. Okay? So, you need to be able to identify valence electrons. I don't really care if you know your core electrons, but you got to know your valence electrons, okay? Because they're what's important, okay? They are what's responsible for all the chemistry. Yes?
So are valence electrons only going to be in the second level, or are they going to be just the outermost? So there's
They're
a third
always
and
the,
a third.
they're always the outermost. So if you go down in the periodic table to where you're in row 3, row 4, those start to be the valence, okay? The good thing is, again, for carbon, we're only dealing with the second row. For most of organic chemistry, you're going to be talking about these orbitals as being the orbitals that contain your valence electrons. Why is it that the valence electrons do the chemistry and not the core electrons?
Because the core doesn't have enough bang to them.
Enough what?
Bang.
Well, okay. I'll buy that. What does that mean?
They don't have energy.
Not enough energy. That's right. They're very low in energy, right? And very low in energy things tend to not be very reactive. Okay? However, another way to think about it is, if you think about it in 3 dimensions, I got the core electrons and then I've got the outer valence electrons. If two atoms, we learned in kinetic theory yesterday, right, that things have to bump into one another. When two atoms come in and bump into one another, is it going to be the valence electrons that get close to each other or the core electrons? It's the valence electrons, right? They're the ones that are able to do the chemistry. That's why we have to be able to distinguish between the two, okay?
So that's the answer between two is the energy they give off.
Sure, yeah. And so we can ignore the core electrons. Again, some of my colleagues would yell at me about that, but it's true. I mean, in terms of all the chemistry that we're going to be talking about, core electrons are just there to be there. The valence electrons are the ones that actually do the work, okay? And they carry everything along. So, we need to be able to determine the valence electrons for atoms. So when you're looking at the periodic table, how do you determine the valence electrons that are in?
I have a question.
Sure.
So the core electrons, are they the one underneath the outermost shell, or are they the lowest?
They are everything below.
Everything below.
Those are core. It just so happens in organic chemistry, it's the 1s orbital, right? But if you went to 3, it would be the 2 and the 1. So, the good news is that you all can figure out the valence electron simply by looking at the periodic table. And so if you look, boron is in group 3. Guess how many valence electrons it has?
3,
How many does carbon have?
4,
How many does nitrogen have?
5,
How many does oxygen have?
6,
Fluorine?
7, and 8.
And it's got a full shell, so it's not reactive, right? But, yeah, so for everything that we're dealing with in organic chemistry, since we're dealing with a very small amount of the periodic table, you can simply look at what group it is in, okay? I will allow you to have a periodic table on the exam. I'll print one out and it'll be there for you. I don't expect you to memorize the periodic table. But the good news is you're only dealing with kind of this little bit right here, right? So you can easily identify the valence electrons. And if you look, everything within that family will have the same number of valence electrons, right? So carbon has 4 valence electrons, silicon has 4 valence electrons, germanium has 4 valence electrons. They're at different levels, but they're still the same number of valence electrons, okay? So, easy to figure out just by looking at the periodic table. You can figure out how many valence electrons you have, okay? All that to say, electrons are what are responsible for bonding, right? And a chemical bond, right, is an electronic thing, right? A chemical bond are electrons that are holding atoms together in some form or fashion. And so for the purposes of this course, we are going to talk about covalent bonds only. But there are 2 types of covalent bonds. There are polar covalent bonds, and there are nonpolar covalent bonds. Okay? And you'll need to be able to identify those. And we'll talk a little bit about that in a moment. But a covalent bond is the sharing of electrons between atoms. And if that sharing is equal, it's nonpolar. And if the sharing is unequal, then it is polar. Okay? We'll talk a little bit about that more as well. All right, so we're going to be talking about those valence electrons only. And the Lewis dot representation gives us an idea of how to assemble and make a structure. Right? So you learned about Lewis dot structures in Chem 106, right? You all talked a little bit about Lewis dot structures. Turns out G.N. Lewis died in the early 1900s somewhere. I can't remember exactly when he passed away. Probably should have won a Nobel Prize, but he was, the rumor is that he was so unliked by a lot of his colleagues that they never nominated him for a Nobel Prize. But think about it. You all learned about Lewis structures. It's got his name on it. And then we're also going to learn in another chapter about Lewis acidity and Lewis basicity, another thing that he developed, both of which, in my opinion, should have won him the Nobel Prize.
Can he get posthumous?
Nobody's going to do that. I don't think he's been gone too long. So here's some examples of electronic structure. Again, looking at boron and phosphorus. If you look at the number of electrons that boron has, right, it's got 5 electrons, 1s2, 2s2, 2p1, right? This is the structure. What you see in the box are the what electrons? The valence electrons. So boron has 3 valence electrons. Can anybody tell me, just take a guess, how many bonds you think boron typically forms? It typically forms 3. Okay. Carbon has 4 valence electrons. How many bonds does it typically form? 4 bonds, right, of some kind. Now that doesn't hold all the time, but it is interesting that the number of valence electrons kind of mimics that, right? If you look at phosphorus, something that goes into the third atomic shell, you'll see that its valence electrons are 3s2, 3p3. So there are its valence electrons. It has 5 of them. And you would give a Lewis dot representation like this. What does this mean?
It's neons.
That's right. It has all of its core electrons are accounted for by neon. So we say it has a neon core followed by its valence electrons. So that's another way to, that's a shorthand to represent it, is to use the nearest noble gas and then give the valence electrons.
Question.
Yeah.
What's the SSP?
What's
The S?
S and P?
Yeah.
Those are the orbitals. So the s orbital and the p orbital. Yep. All right, you all learned in Gen Chem quite a bit about things that were ionic. You all talked about a lot of dead salts, right? Sodium chloride you talked about a lot. You probably talked about sodium or potassium carbonate. All of those molecules or compounds exist because something stole an electron from something else and became positively charged, and something else became negatively charged, right? And those opposite charges attracted. Those were what we called ionic bonds, okay? Again, most of organic chemistry doesn't deal with ions. We deal with covalently bound stuff, which is kind of good. And a chemical bond that results from the sharing of electrons, we always call that a covalent bond. That's what we're talking about here. And so anytime you can have an atom and another atom come together and share a pair of valence electrons, that's going to form a bond, okay? So if you think about anything that is sharing an electron or sharing a pair of electrons, so like if you think about hydrogen has 1 valence electron, and if you think about fluorine, which has 7 valence electrons, if I can count, right? Here's an opportunity for this electron and this electron to share and form a bond. So hydrogen fluoride forms a bond between the hydrogen and the fluorine because each one of them has a lone electron that could pair up with one another and form a bond. It is a covalent bond. It's not ionic. They are sharing the electrons, okay? This is a molecular orbital diagram of how bonding occurs. We are not going to spend a whole lot of time with molecular orbitals, but what I want you to understand is that bonds, while we think of them as like springs that are holding atoms together, that's the way I like to think about them, okay? They're really molecular orbitals where electrons exist. So we talked about the atomic orbitals that come in from the atoms, but when they start to interact with one another, you start to create what are called molecular orbitals. And this is the simplest example for hydrogen. So I've got hydrogen with its 1 electron and hydrogen, another hydrogen with its electron coming together to form H2. This is the molecular orbital diagram for that. So here we have hydrogen. It has 1 electron in this 1s orbital. The other hydrogen has 1 electron in its 1s orbital. And when they come together, they form 2 new so-called molecular orbitals, and both electrons go into the lowest orbital. And we call that sigma. Sigma bond is a single bond, okay? So it forms a single bond between both of those hydrogens, and both of the electrons are now in the lowest energy molecular orbital, which is represented as a stick. That stick between the two hydrogens is the molecular orbital, the sigma molecular orbital that's holding the two things together, okay? And I like to think of them as sticks or springs, right? I don't like to look at those diagrams and it gets kind of confusing, especially after hydrogen, okay? But what I want you to know is that bonds are really nothing more than molecular orbitals. So another thing that you need to know is that I have a 1s orbital here and a 1s orbital here. For every orbital that you bring together to form a bond, you have to create that same number of molecular orbitals. Okay? So, this is one orbital, this is one orbital, that's a total of 2. So I have to create 2 molecular orbitals. One of them is called the sigma, one of them is called sigma star. This is a bonding orbital, this is an anti-bonding orbital. Okay? So think about this. Hydrogen and helium are exactly in the same period, right? Period 1 of the periodic table, right? So helium, how many electrons does it have? It's got 2, right? So it's like hydrogen with 1 more proton and 1 more electron. So if I tried to bring 2 helium atoms together and form a bond, that doesn't occur. Why? Based on that diagram, why would you say that helium can't form He2?
Because of the
Because it has more
anti-bonding.
than 1 electron.
That's right. So I would put the first 2 electrons down here and form a bond, but I've got 2 more to take care of, and where would they go?
Anti-bonding.
Into the anti-bonding orbital, right? So those electrons would ultimately break that bond that forms, right? Overall, there's no bonding characteristics between that allow this to happen, okay? So you can't have dihelium. You can have dihydrogen, but you can't have dihelium, okay? Because the helium is stable, and this explains that whole thing just by drawing a few little lines, okay?
What does the E stand for on the side?
Energy. So lower energy, higher energy. Good question. We also talked a little bit last time about trends in the periodic table, and we started talking about electronegativity briefly, and you all did a very good job telling me about general trends. So as we start at the lower left, we're not very electronegative, and as we go up to the upper right, we're much more electronegative, right? So we know that fluorine has an electronegativity of 4. It's the most electronegative element on the periodic table, and I forget what the electronegativity is for francium, but it's close to 0. Okay, so not very electronegative, very electronegative. And you will need to be able to look at a bond and look at the electronegativity of the atoms in that bond to determine whether or not the bond is polar or not. So for example, hydrogen fluoride, it's a covalent bond because it's sharing a pair of electrons, but is it polar covalent or is it nonpolar?
Polar.
Very polar, right? So I've got a very electronegative atom and a not very electronegative atom. So what does that mean? Does that mean that we have equal sharing of these electrons?
No.
Not at all. Fluorine is hogging them, right? It's pulling more electrons towards itself in that bond. So if you were to look at that bond, you would see that more of the electrons are sitting around fluorine than around hydrogen. And we would say that this is a polar covalent bond, okay? So I think we can skip that slide. So here's an example. These are diagrams of what a bond kind of looks like if you generate it in a computer. And what you can see, so these spheres represent the atoms, and the clouds around them represents the electron density. Don't worry about that too much. But what you need to know is that I hope by looking at this you can see that fluorine, F2, is a covalent bond, but it is very nonpolar. This side looks identical to that side. Right? If I take F2 and I look at it like this, and then I turn it 180 degrees, I can't tell that I did anything. They look the same. Okay? However, notice that the hydrogen fluoride looks very different on both ends. And in these computer graphics that get generated, red is more negatively charged, blue is more positively charged, right? So what is this telling us?
It's very off balance.
It's very off balance. What does that mean?
They don't do that.
I apologize.
It's okay.
Fluorine's more electronegative.
It's more electronegative. It's pulling more electrons to itself. That's why the sphere is a little bigger around fluorine. Notice the hydrogen, the sphere is less, and it's more blue, right? So I would say that the hydrogen has some positive character to it. It's got a little bit of a positive charge on it. And I would say that the fluorine has a little bit of a negative charge on it, okay? That is a polar covalent bond, okay?
How do you know if it's polar or not?
If the electronegativity difference between the two atoms is greater than 0, it's polar. If it's 0, it's nonpolar. It's the easiest way to think about it.
For some reason, I feel like, I remember Jim Kim that, there was a third one that was like, you know, you had the polar and non-polar, but there was one more. But the way we done it was, you take the electronegativity of one and subtract it from the other, and if it fell in between a certain range, like 0 to something, it was.
There are some additional things within that continuum. There are things that are more polar than not. There are dative bonds, which may be what you're getting at, but we're not going to cover that at all.
So we're just gonna focus on it's either 0 or it's half.
Well,
of it.
certainly there's some stuff in between.
Right, that's what I'm
But
talking
really
about.
what I'm interested in, can you identify whether it's polar or nonpolar? So if it's around 0, we're going to consider it to be nonpolar. If it's, the difference is quite a bit away from 0, then we're going to consider that to be a polar bond.
Right, so if it's like, you know, fluorine and, oxygen.
Oh, that's going to be polar.
Right.
Not going to be hugely polar, because oxygen itself is electronegative.
Right. Because they're so close and it's pretty
Yeah,
close.
so the further away you are on the periodic table, the more polar your bond's going to be. The closer you are, the less polar it's going to be. That's certainly true. Yeah. So this also applies to other molecules. So there's hydrogen chloride. I'm sorry but that's an H. Looks very similar to HF, right? Here's water, right? You'll see that water is polar. It has polar bonds. Hydrogen has an electronegativity of around 2-ish. Oxygen has an electronegativity of about 3.5 or so. So each one of those bonds are polar. But notice that the dipole isn't in the bonds. It's actually in the middle, right? So water is a polar molecule because of its shape. You can have molecules that are nonpolar that have polar bonds, and we'll see that in just a moment. But because water is bent, it has a dipole. The oxygen is more negative, and down here between the two hydrogens is more positive. So you end up with a dipole. This has very, very significant consequences on why we're alive. If water were linear, life couldn't exist. Believe it or not, because water would go from being polar to nonpolar. Water would boil at room temperature. There would be no liquid water on Earth. Water wouldn't be able to dissolve salts like it does. Shape, what did I tell you on the first day? Shape is equal to function. Shape is very important, okay? And so if you draw water linear, you're wrong, okay? Water is bent. This is acetone. Okay, don't worry too much about the naming yet. We'll get into names later on. But kind of has a similar shape to water. Obviously, this is an organic molecule, whereas water is inorganic, right? It has a dipole that's kind of looks like the dipole of water. For those of you who wear nail polish, this is probably what you use to take it off. Acetone will dissolve paint. But it will also dissolve paint and it will also wash off in water because of its shape. So it works really, really well for those types of purposes. So again, shape matters. Now let's look at carbon dioxide. I think you all will agree that carbon dioxide, each CO bond is polar. Oxygen, again, has an electronegativity of around what? About 3.5. Carbon has an electronegativity of around 2-ish. Forget the exact value. Right? So the carbon-oxygen bond is a polar bond. But because carbon dioxide is linear, the dipole in this direction is canceled by the dipole in that direction. So if I take carbon dioxide and I look at it here, I see the negative dipole. If I flip it the other way, 180 degrees, I still see a negative end of the dipole. So no matter how I turn it, all I see is negative. I don't see both poles. And so it is a nonpolar molecule. It is a molecule that contains polar bonds, but is overall nonpolar. This is very important. Carbon dioxide is used to decaffeinate your coffee, for example. They liquefy carbon dioxide, they mix the beans with it. The caffeine will dissolve into the carbon dioxide, and then they separate it from the bean. Okay? For those of you who like to drink decaffeinated drinks. If it were polar, that wouldn't happen. It needs to be this nonpolar molecule to remove the caffeine. Okay? And so, again, shape matters.
So what's the difference between a polar bond and a polar molecule?
Let me put it to you this way. All polar molecules have polar bonds, but not all molecules with polar bonds are polar. So again, you have to look at the whole shape. I've got polar bonds in carbon dioxide, but since the dipole in this direction is canceled by the dipole in that direction, it cancels out, and it's not polar. Whereas HF, you've got a dipole that's not canceled by anything else, and so it's polar. Does that make sense? Okay. So when drawing Lewis structures, there's a few rules that you need to live by. We're always going to be dealing with the valence electrons. We've already talked about that. You know that. And so you can just get those from looking at the periodic table. You know, for every carbon you have, when you're doing a Lewis dot structure, you're going to have 4 valence electrons for each carbon. You're going to have 6 for every oxygen, right? And you're going to write down a skeletal structure, and you're going to start connecting stuff. You all did this in Chem 106. Okay, so I'm not going to spend a whole lot of time on it. But you need to know that in the normal world, which in my view is organic chemistry, we're not talking about things that are esoteric, you will find that hydrogen will form 1 covalent bond. You will find that the halogens, chlorine, fluorine, bromine, iodine, will form 1 covalent bond. You will find that oxygen will typically form 2 covalent bonds, that nitrogen will form 3 covalent bonds, and that carbon will form 4 covalent bonds. So when you're drawing structures and you go, wait a second, my hydrogen has 2 bonds, you know you're probably wrong. Okay? Now, can I show you examples of where hydrogen has 2 bonds? Yes. If you want to take advanced chemistry classes, we can get into those special situations. But for life, for the things that you all are going to be studying, it's irrelevant. It's just, it's kind of, you know, if you tell a chemist carbon can only form 4 bonds, we're going to go out and try to find a way to make it form a 5th. And they've done that, okay? But it's esoteric kind of stuff, okay? Stuff that people just take as a challenge to try to find. But you need, yes, ma'am?
Are we going to be drawing Lewis structures?
You will be doing some of that, yes. Okay. So you all need to memorize that. Hydrogen has how many covalent bonds?
1,
Carbon,
4,
nitrogen,
3,
oxygen.
2,
Good. Halogens?
1.
All right. Good deal. So let's look at an example. Let's draw a Lewis structure. Okay? Now the Lewis structure, you all typically need to know at least how the atoms are connected. I will give you that most of the time. Okay? I can't think of an example where I won't. This has to be determined experimentally. But typically the rule that you probably learned in general chemistry is that the least electronegative atom was the central atom. You probably learned that in Gen Chem. Okay? And so for phosgene, COCl2, oxygen's very electronegative, and so is chlorine. Carbon's the least electronegative, so it's in the middle. Phosgene is connected carbon, oxygen, chlorine, chlorine, like that.
Our play rule is number 8, right?
Pardon?
Oh, okay, isn't that?
Yeah, that's right. Yep, the rule of 8. Yep, and which works for things only in the second period, right? So keep that in mind as well. All right. So we've connected the atoms together. We've got a total of 24 valence electrons that we have to account for, right? I've got 4 from carbon. I've got 6 for the oxygen atom, and I've got 2 chlorines, and chlorine has 7 valence electrons. So that's how I get a total of 14. I do the arithmetic, I add that up, I've got 24 electrons, okay? So what is 24 minus 6? How many electrons do I have left to account for? Got to take care of 18 electrons, right? So now I got to start adding electrons. Where am I going to start adding electrons around?
The highest electronegative.
Pardon?
I'd say the most electronegative.
Okay, and why would you do that? Why would you go with the most electronegative and not the least electronegative?
Because they attract electrons the
It
most.
just kind of makes sense, right? If you're an electronegative atom, it makes sense we'd put the electrons on you first because you're the most electron hungry, right? All right. The issue here, though, is what? Oxygen and chlorine are pretty close in electronegativity, so it doesn't really matter where you start. Okay, so what are we going to do?
Start putting dots around to represent the electrons around the
All right.
chlorine and oxygen.
Very good. We're going to start adding electrons, right? So I've taken care of that. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18. So 18 plus 6 is 24. I've accounted for all of my valence electrons, right? But is it complete? Why not?
Carbon doesn't have
Yeah, carbon doesn't have 8 yet, does it? So what do I do?
any, either take 2 off of one of them, either chlorines or oxygens, and make a double bond.
And share between, right? Yeah. And it turns out that it's between the carbon and the oxygen. Oxygen is just a little less electronegative than chlorine. And you end up making a double bond. So now if I add everything up, everything has an octet. So if I look at this, it's got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, and everything is good. We're happy to go, right? All right. So we've obeyed the octet rule. We've just built a Lewis dot structure for phosgene. Does anybody know what phosgene is? Anybody ever heard the word phosgene? It's a very useful molecule, actually. We've got some in solution. I think I still have some up in the lab. But it gained notoriety in World War I as a chemical agent that was used on the battlefield. Phosgene has a bad reputation now as being extremely lethal. It is lethal, it is deadly, but it is not the most deadly thing I've ever worked with in my life. In fact, it was a very poor chemical warfare agent. And then part that's why the German side didn't win the war, because they were using things like phosgene that, while it was terrible, was not as deadly as people had thought it would be. Yeah.
I have a question. So in a previous chemistry class, we were only told that like certain elements can form double bond and triple bonds. Do you want us to? Oh, it was like only carbon and nitrogen can form a triple bond.
Well, it turns out that that's only partially true. But in terms of organic chemistry, carbon, oxygen, carbon, nitrogen, those types of things can form multiple bonds quite easily. Other atoms can form multiple bonds as well. There's actually even atoms that will form 4 bonds. Okay? It's called delta bonds. But we don't need to get into that.
So like is that still like a general rule?
It's a good general rule, yeah. It's not a law, but it's a good general rule. So when we're thinking about making multiple bonds, carbon, oxygen, nitrogen is a good rule to play with. Yep, very good. The other thing you've got to do is you've got to determine the formal charge. You may or may not have done this in Gen Chem. In your book, there is a formula for calculating formal charge. Ignore it. You don't need to memorize a formula. Formal charge is nothing more than the number of valence electrons an atom comes in with and how many it formally owns. It's just subtraction. And if you can draw a circle, you can figure it out. You don't even have to memorize the formula. All right, so oxygen comes in with how many valence electrons? 6. Comes in with 6, right? So, okay, I want to know what the formal charge of oxygen is. It comes in with 6 valence electrons. Now let's determine how many valence electrons it owns, and that's what the circle does. Everything that's inside that circle belongs to that atom. The lone pairs belong to that atom. How many lone pairs do I have?
2,
Which is a total of how many electrons?
4.
All right, so it owns those 4. Now notice that the circle cuts the bond. So what does that mean?
Means it loses 1.
One of the electrons from each one of those bonds belongs to oxygen, and the other belongs to the other atom, in this case carbon. So in this bond, one of these electrons belongs to oxygen, and in this bond, one of those electrons belong to oxygen. The other 2 belong to carbon. So how many does it own?
6.
So the formal charge is
0.
0. It has a formal charge of 0. You can go through and do the same thing for all of the atoms, and what you would find is that every one of those atoms has a formal charge of 0. So if you know how many valence electrons come in from the periodic table and you know how to draw a simple circle, you can figure out what the formal charge is of any atom. Okay? You don't need to remember that it's the number of valence electrons minus the number of bonding pairs minus 1/2. Just draw a circle. It's easier. Okay? Any questions about that?
So what do we use formal charge for?
So you will need formal charge when we start talking about some reaction mechanisms. Some atoms, so for example, let's look at this one. Let's just work one on the board. So let's look at nitric acid. Nitric acid is HNO3. It's a strong acid. Let's put in all the electrons. Now, overall, nitric acid is neutral. Okay? What is the formal charge of the nitrogen? How many electrons does nitrogen come in with valence? It comes in with 5 valence electrons, right? All right, so let's put a 5. Now, how many does it formally own? 4, right? So its overall formal charge is what? +1. So this nitrogen is actually positively charged. Okay? What about this oxygen? 0. What about this oxygen?
0.
What about this oxygen?
0.
-1. Why?
It still has 1.
Oxygen comes in with how many?
6.
Okay, and we're going to subtract how many? 2, 4, 6, 7, right? So that's really the Lewis structure. Lewis structures, you need to show the formal charges. Okay?
You're not worried with the hydrogen?
We could calculate that too. We could calculate it for every atom. I'm just not. What's the formal charge on that hydrogen? 0. Right? But it's a polar covalent bond, which accounts for its acidity. And we can get it when we start talking about acids and bases. We'll get into that a little bit more. Okay. Any other questions? Well,
What do we use it for? Like, are you gonna ask us maybe like calculate the formal charge?
I could. I could ask you to calculate the formal charge. If I asked you to draw a Lewis structure, I would expect it to be drawn with all the dots and all the bonds and all the formal charges for any atom that had a formal charge. Usually any atom that has a 0 formal charge, we don't ask you to put a 0 on it.
So we write that into the structure after
do.
we figure it out.
You do, that's right. So this is the correct Lewis structure for nitric acid.
Do we write -1 or just minus?
That's a matter of taste and preference. I always write the number, but if you wrote just a single minus, I would count that. If it was a -2 charge and you put minus, I would count it if I could tell that it's actually minus and not just one big minus. So I always recommend people put the number, but that's just a matter of taste. There is no real reason for that. All right. You all need to know these bonding patterns. You need to be able to roll these off of your head. Okay? because you're not going to have enough time to always build a Lewis structure and to always count the formal charges on everything, right? So what do you need to know? You need to know that carbon will form 4 covalent bonds, and it's got 4 ways it can make them. It can make 4 covalent bonds as 4 single bonds. And, this means bonded to anything. It can form 1 double bond and 2 single bonds. It can form 2 double bonds, or it can form a triple bond and a single bond. All of those are possible for carbon. Nitrogen can form 3 bonds and have a lone pair. It can form a double bond, a single bond, and still have a lone pair, or it can form a triple bond and have a lone pair. Oxygen can either form 2 single bonds, or it can form a double bond. That's typically how it likes to do its work. Okay? And then the halogens almost always form single bonds. You probably learned some examples in Gen Chem of where halogens can form multiple bonds. And it's true, it can. Not in organic chemistry so much. Okay? They typically form just a single bond.
Do we need to memorize the number of valence electrons for each one, or like the shapes? I don't understand.
Well, you're going to need to know both eventually. But right now, I'm really just interested that you know the patterns of the bonds.
The patterns?
Mm-hmm. So you've got 4 bonds for carbon, and it can do it 4 ways. You've got typically 3 bonds for nitrogen, and it can do it 3 ways. You've got 2 bonds types for oxygen, so on and so forth.
So you don't ever give carbon a lone pair?
That 99% of the time that is correct. I can show you examples of where carbon does have a lone pair, but it's not typical. We will probably not be covering any of that in this course. But yes, I can show you examples of where carbon actually only has 3 bonds because of where carbon sits on the periodic table. But those are highly reactive things that only fleetingly exist, and they're important in chemistry, but not yet.
So why do we need to know the different shapes?
Because shape is equal to function. Right? So you're going to see in functional groups that you will have different types of bonds in those functional groups. So a carbon that is doubly bound to an oxygen belongs to a particular functional group. And functional groups tell us how that molecule will function and how it will react and how it will do its chemistry. Okay. You also probably learned a little bit about resonance in Gen Chem. Does anybody remember about resonance? Okay. So, resonance exists because there is a flaw in Lewis structures. And if you think about Lewis structures, and let's just take the example that we're given up here. So H bonded to a carbon, double bonded to an oxygen, bound to a nitrogen, bound to a hydrogen. It's got its lone pairs, and there's a negative charge here. All right, so nitrogen comes in with how many?
5.
And it owns how many? So it's negatively charged, right? All right. If you look at a Lewis structure, the electrons are assigned to a specific atom, right? But that's not always true. In fact, I can push these electrons here and make a carbon-nitrogen double bond, and I can break one of those bonds and put those electrons on oxygen and create what's called a resonant structure. It looks like this. This arrow tells me that I'm taking this pair of electrons, and it's a pair because I'm using a double-headed arrow. I'm moving them from just being on nitrogen to being between the carbon and the nitrogen to form a bond. And I'm taking this pair of electrons in this bond, and I'm moving them up to oxygen to be a lone pair. Which one of these is correct? Both are correct. Both are correct. Okay? In fact, the molecule doesn't look like this, nor does it look like this. It looks like something in between. Okay, and we call that something in between a resonance hybrid, which we'll learn more about later. Don't freak out about it. Okay? This is correct. This is correct. But one of them is more correct than the other. Can you tell me which one? The one on the left or the one on the right?
I suppose it's the one on the right because
Why?
I guess oxygen is more electronegative than nitrogen.
That's right.
And in the right, the nitrogen's formal charge is 0.
That's right. So I've got a negative charge on nitrogen here. Here I've got a negative charge on oxygen. Oxygen being more electronegative, it's going to be more prone to having that negative charge, right? It's going to be more stable. So while these are both correct, this one is more correct. And in fact, the resonance hybrid, if you were able to look at it in a magic microscope, would look more like this than like this, okay? And what do I mean by that? If I was to look at a magic microscope, I would see that the carbon-nitrogen bond is a little shorter, because it's a double bond, than what you would expect it to be here as a single bond. And I would see that the carbon-oxygen bond would actually be a little longer than you might have expected, okay? And again, we've got magic microscopes that can do this kind of stuff, called magic microscopes, but we do have ways of doing this kind of work.
So the one on the right is more right because oxygen is more electronegative than nitrogen?
Bingo. Okay. That is correct. All right. Now, if we think, now let's think about carbon. Let's start thinking about shape a little bit. And let's think about the simplest organic molecule that exists, and it's called methane, CH4. 1 carbon, 4 hydrogens. You all use this in natural gas. If you heat your house with natural gas, if you cook with natural gas, you're burning methane. Okay, it's what we use for a lot of our energy needs. If you look at carbon over here on the left, this is the ground state for carbon that we just talked about earlier, right? This is the valence electrons. 2 of them are in the s orbital, 1 in the 2px and 1 in the 2py orbital, right? How many bonds would you think carbon could form if it existed like this? 2, maybe 3, right? I could share an electron with another hydrogen here, and I could share an electron with another hydrogen here. And maybe I've got a proton, H+, that comes around and forms a bond there, right? Maybe. All right, so 2, maybe 3 bonds. But what do we know about carbon? It forms 4, right? Why is it? If carbon comes in with these, why does it form 4 bonds? And it's because the atomic orbitals can hybridize. And this is going to hurt your head a little bit. I'm not going to talk about any of the quantum crap with it. Okay? But it's hybridization. And what happens is carbon can get excited and promote an electron from the 2s orbital to a 2p orbital. It takes energy to do that. But now I've got 4 single electrons that in theory could form a bond, right? Okay, so we've taken into account 4. But what's the problem? We've got px, py, and pz, right? How are they oriented with respect to one another? They're on the axes, right? They're 90 degrees. When I look at methane in my magic microscope, is that 90 degrees?
Yeah.
Nope, not 90 degrees. It's 109.5. It's the shape of the tetrahedron. So what happens? These orbitals do what we call hybridize into what we call sp3 orbitals. Okay? And we'll talk a little bit about that in a moment. But an sp3 orbital is shaped to where they point at 109 degrees. And that's how you get the shape of methane. If we look at ethene, which is another simple organic molecule, CH2 double bonded to CH2, okay? Each carbon has 4 bonds, but the shape is very different. It doesn't look anything like methane, right? It has a different shape. It's planar, right? If I made a model of it, it would sit nice on the table and just lay there, be nice flat, right? We would get that from Vesper theory. Let me go through this real quick. Okay, so what's happening, right, is you have the ground state of carbon that gets electron promoted. One of these electrons should have been up there. I don't know why it didn't pop up there, but imagine that one flipping and going up there. And then those become hybridized. Okay? In methane, it hybridizes to sp3, 4 sp3 orbitals that are degenerate. In ethene, you get 3 sp2 orbitals, and then the 2pz orbital is left unhybridized. Okay? We call those sp2 orbitals. Don't freak out about this. We'll go through this more in detail when we get to alkenes. But it's why you have the double bond. This electron here is why you have the double bond. Okay? Now, I will expect you to be able to identify the hybridization of a carbon atom.
Can you explain hybridization again, like what do you mean by?
So hybridization occurs when the atomic orbitals mix together to create new orbitals that will allow different shapes to occur. It's a little, I hate to say magic because nothing's magic, but it all comes out of quantum physics. And so for my purposes, that really is kind of magic, right? But we know that methane has these 4 bonds that are in the shape of a tetrahedron, and I can't get to that shape from the atomic orbitals that are just on carbon. So I know that a hybridization had to occur in a way that gave us new shapes. Okay?
And so how do I identify that?
Okay, I'm going to show you the easy way to do this. So let's look at an example. So let's say we have carbon dioxide. And I ask you, what is the hybridization of this carbon? All you have to be able to do is count the number of multiple bonds that are to that atom. Okay? So notice on the number of multiple bonds side of the table, it's 0, 1, 2. All you got to be able to do is count 0, 1, 2. And on the hybridization side, no, it goes sp3, sp2, sp1, which is sp. Okay? Notice it goes 3, 2, 1. So 0, 1, 2, 3, 2, 1. You can figure it out. So how many multiple bonds are to this carbon? 2 of them, right? So it must be it's sp. It is an sp hybridized carbon, meaning that one s orbital and one p orbital hybridized to make the sp orbitals. Okay? How about this carbon? How many multiple bonds do we have? So it is sp2, right? If one multiple bond, then it's sp2. What about this carbon? No multiple bonds, 0, so it's sp3. Tetrahedral, linear, trigonal planar. Okay? And you can have multiple types of carbon in an organic molecule. So here's an example. Notice I got 2 carbons that are triple bonded, and I've got a couple of carbons that have all single bonds. That particular molecule contains both sp and sp3 hybridized carbon atoms. Again, the magic of carbon being able to connect in different ways. Okay? All right, last slide of the day. Getting at the end here. You have a list in your book of functional groups. You need to memorize those functional groups. I knew we wouldn't have time to go through the whole list today. We'll pick up with that again on Monday. But here's some of those functional groups in real organic molecules. I don't like TVs because they don't show my slides. So here we have a functional group. This is called an amide. You'll need to memorize that. Here's another functional group. This is called an ether. Anytime you have an oxygen that's connected to 2 carbons through single bonds, that's called an ether. Anytime you have a carbon connected to an OH, that's called an alcohol. Anytime you have a nitrogen that has at least 1 hydrogen on it and 1 or more carbon atoms like this, and its lone pair, we call that an amine. All of these functional groups come together and connect to make things that are useful. This is atenol. It's an antihypertensive agent. This is Virusept. This is an anti-HIV agent, right? But notice all the different types of functional groups. We've got amides, we've got amines, we've got alcohols, we've got a different type of amide, we've got sulfides, we've got alcohols, we've got these aromatic rings. All of these things come together. They're called functional groups. I know the chemistry of alcohols. You will learn the chemistry of alcohols during this course. I know that alcohols can form ethers. I know that alcohols can be oxidized into other functional groups. I know that, and that's what, if you drink beer or liquor, that's what gets you the buzz. It's because it gets oxidized in your liver, right? It makes toxic compounds. That's why you get the feeling that you get, okay? So, I highly recommend you all make flashcards of your functional groups. Yeah.
So what are?
Pardon?
What are functional groups?
Functional groups are, so notice here, would you say that that looks the same as that one?
No.
It doesn't look exactly the same, but it's still a carbon attached to an OH. The chemistry of this functional group is going to be similar to the chemistry of this functional group, even though it's in a different molecule. So because I know the chemistry of the functional group, I know what the chemistry will be regardless of what molecule it's in. They have a particular function. And we'll learn those functions as we talk about different things in the different
Do
chapters.
you want us to draw them out or by name?
I want you to know by name and by sight.
So they, like,
Good.
the alcohol, the functional group is an OH and that shape thing on top of it?
It is an OH that's connected to a carbon atom.
That is connected to a
Carbon atom.
carbon atom?
Yep, that is a carbon.
This is the one.
The line is a carbon?
Yeah, we'll talk about that next time.
Is it only those 5?
Huh?
Is it only those?
No, you got a list in your book of
This is
probably,
the one that you're talking about.
yeah,
Oh, you know the page.
there's at least 7 there, right? And then
Yeah.
there's probably some others that we'll talk about. So, yeah, it's on that page in the book. Don't worry, we'll get there.
Still waiting.
All right, I'm giving you 3 minutes back. I'll see you on Monday.
Hopefully I won't. I woke up exactly 9:30. I was like, God. I woke up at 8:29. I was like, oh, I got 30 minutes. That 30 minutes turned to an hour.
Yep.
Did I miss anything at the beginning of the class?
Yeah. You'll be able to see it in the video.